Hi guys, welcome to Chapter 2, Hamilton Circuits. Our first chapter was actually all about Euler, and Euler's about edges, and because of Euler's theorem, it's easy to know if an answer needs to be found or not, and if you have to Eulerize, we simply try to make it work. Excuse me. Because it's actually quite difficult. So, Hamilton circuits is all about vertices. And it's hard in the sense that we want to do it, but to try to make it work, it's quite difficult to be good. So we're going to develop some algorithms, processes by which we're going to solve some problems, but we're going to have no idea if they give us good answers. We just try to see how it works. If you remember from Eulerization, we had that one test that if half the odd valences was exactly the duplicates, then you did a perfect Eulerization. But if it fails, it doesn't mean you did a bad one, it just means you don't know. So Hamilton being about vertices, let's start with an example right out of the book. I try not to do that too much since you can follow the book along, but this time I want to show what the book does here. So here's a graph where the dots are the vertices, nothing unusual, and you'd like to visit each of the vertices. So in this case, just think about the edges actually being roads, the vertices being towns, and you don't want to check the roads for their quality or snowplow the roads. You just want to make sure you visit every city to meet with your clients or something. So clearly, one route that will visit every city is this one, and you can get back home. So there's what's called a Hamilton circuit. It visits every city exactly once. Now, just realize you go in and you leave, so that's what we mean by exactly once. But now I can do it a different way. I mean, there's no reason to say you have to do it that way. How about this way? Did I mess that up? Yeah, I did. Didn't mean that one. So just like a bow tie. Don't follow that one. So there's more than one way to do it, just like there's more than one way to Eulerize. But of course, then the question is, if there's more than one way to do it, which is a good way? Now, since most Hamilton problems talk about visiting the vertices, the edges are usually a matter of building something, traveling something, the hours needed to do something. So the edges represent a process that usually has a weight associated with it. So a map like this has more than one solution. We can't really judge the solutions in a real life situation unless we add some weights to the edges. So we might do something like this and say this is the hours it takes to travel these edges. And now if you compared the two routes, circuits, let's do the green. I got to put a number in here. Let's do the green one. The green one would be 3 plus 1 plus 4 plus 3 plus 2 plus 3 plus 1 plus 2 plus 2 home. And so that would be the cost associated with following the green circuit. Now, if we were following the pink circuit, what would the cost be? Well, let's follow the pink circuit here. Let's do up and around. It'd be 3 plus 3 plus 4 plus 3 3 plus 2 plus 3 plus 1 plus 2. It looks to me like this one, the pink one, is actually quite a bit longer, but I'm not sure. Let's see. 2, that's equal 4 minus 3. It's 3 longer to go on the pink one, so the green one was better. But is it the best job? I don't know. So what we're going to do is we're going to look at a traveling salesman or postman trying to find the right way to walk to visit all of his post boxes, but they've got to get back to where they started. Now, the book has a very simple example, and it's also a nice example because it points out how nice it is to realize that models are truly models, yet they contain the information necessary, and lots has been thrown away. So here's 4 cities: Minneapolis, St. Louis, Cleveland, and Chicago. And you know what? The way this is set up, it's not possible to be orientated like a real map. Cleveland is not north of Chicago. Minneapolis is not south of Cleveland. Minneapolis is west of Chicago. St. Louis is not northwest of Chicago. And this map is just relationally wrong. But I can put in information that relates factual information that doesn't make use of the inappropriate direction. It just simply says the edge represents a relationship, and here it's 349 miles between Chicago and Cleveland. Here it's 300 miles between St. Louis and Chicago, and here it's 425 miles between Chicago and Minneapolis. It's 562 miles between Minneapolis and St. Louis, and it's 774 miles between Minneapolis and Cleveland, and last but not least, it's 541 miles between Cleveland and St. Louis. You can look these up on a maps or a Rand McNally atlas. These are probably quite accurate, close enough, but we don't care about the relationship of east, west, north, and south. We just care that these are the known distances between these towns. Let's put you based in Minneapolis and you want to go visit each of the cities to meet with your clients. Well, obviously, there's not that many paths you can follow. I mean, there's only 3 choices for Minneapolis. If you pick one of those cities, and then there will be 2 choices, you probably could map them all out. In fact, let's do that. Let's create something called a tree. Start with Minneapolis here, and you can pick Cleveland, you can pick St. Louis, or you can pick Chicago. So there's your choices. Now, when you did Minneapolis to Cleveland, then your 2 choices would be St. Louis, Chicago. If you're in St. Louis, your 2 choices would be Cleveland and Chicago. And if you're in Chicago, your choices would be Cleveland and St. Louis. And now if you did Minneapolis, Cleveland, St. Louis, there's only 1 choice left, Chicago. If you do Minneapolis, Cleveland, Chicago, there's only 1 choice left, St. Louis. And maybe you guys started seeing a pattern. What was here, the other 2 went below. What was here, the other 2 went below. What was here, the other 2 went below. What was here, the other one went below. It actually can be built quite automatically. So here are different routes that you can take. And now let's make it a circuit. Let's get home, back to Minneapolis, 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 back to Minneapolis. And there are actually 1, 2, 3, 4, 5, 6 ways to drive these 4 cities and get home from Minneapolis. Now we can just put in the numbers of how long they are and figure out which one's longest. This tree diagram is called brute force. Brute force means we write down every single possibility. And I want you to notice that there are 4 cities, which leads to 3 choices, 2 choices, 1 choice. You get the number 6. If there had been 5 cities, that would have led to the first 4 choices, 3 choices, 2 choices, 1 choice, which would have been 24. This calculation is called a factorial. A factorial grows very rapidly. If you take out your calculator and try to do something like 71 factorial, and that's the symbol to do it, your calculator could blow up. No, not really, but it will give you an error. Now, if you take out your Apple iPhone or Google, you can put in numbers like 129 factorial, and the answers get so large, it actually tells you the numbers like 117 digits long. The number is so large, we don't even have a name to read it anymore. It's billions, trillions, quadrillions, zillions, Googleplex. I mean, you go on and on. There are fancy names that go up quite a long ways, but these numbers are so large it's incomprehensible. If you had 129 cities, to make a tree would produce a tree so big that just to write it down with a computer working really fast, it wouldn't finish in the lifetime of the universe. The computer couldn't solve the problem. The brute force algorithm, which basically means find everything, is very slow. Amazon, Walmart, tons of shipping companies, the USPS, the UPS, they hire mathematicians and computer scientists to work on this problem because they have hundreds of stores across the country, distribution sites, and they've got trucks moving. They need these people to get stuff around and distribute them. And the problem is almost untractable. So they run these massive computers and they get an approximately good answer. What they do is they've created an algorithm to solve it. I'm now going to demonstrate what we call a greedy local algorithm. It's greedy because it's going to try to do the least amount of work in this case. It's local because it's only going to make decisions based on some of the information. And lastly, it's an algorithm because it's repetitive and cycles with the same questions over and over and will produce an answer. So our picture looked like this. And here was Minneapolis. And if you look at the map, I want you to actually pretend you're in Minneapolis and ask, of the three cities, Cleveland, St. Louis, and Chicago, which one was the closest, or is? Well, Chicago is. It's 425 miles away. So I'm going to make you actually choose right now, with only these three pieces of information, that you're going to go to Chicago. That makes it local because you only use three pieces of information, not all. It's greedy because we're driving the least amount of time, so you're getting more sleep. You're making that decision. So now you think of yourself as in Chicago. You want to visit every city exactly once. You can't go back to Minneapolis, therefore. So you have two choices. You're in Chicago, and you say, well, between St. Louis and Cleveland, which is the closest? Well, St. Louis is 300 away, which is less than the 349 to Cleveland, so you drive to St. Louis. Again, it's local because you only considered two pieces of information. Now you're in St. Louis, you've already been to Chicago, you've already been to Minneapolis, you're forced to go to Cleveland, and you're forced to go home. So these last two steps in this algorithm are forced on you. You didn't get to choose them, and it actually made you travel some fairly big pieces of roads there, but there's your path. This is called an algorithm. Each time we said, where are we? What's closest I haven't been to? Go there. Repeat. Now, what happens if we had started in a different spot? What happens if, let's say, we were in Cleveland and say, we want to find this? Well, if your starting point had been Cleveland, let's take a look at that algorithm again. If you had been here to start in Cleveland and you looked at the three distances from Cleveland, there's 740, 774, 541, and 349. you would have immediately driven this route from Cleveland to Chicago because it was the shortest 349 miles. So I want you to notice this algorithm is going to finish, but it's definitely going to be different than if you had started in Minneapolis. So one of them is probably better than the other. Now, when you're in Chicago and you have to pick between Minneapolis and St. Louis, turns out St. Louis is only 300 miles away. That's the shortest of the two choices. And now the last two are forced on you because you have to visit Minneapolis and you have to get home. So, if you started in Minneapolis, you would have done this route. If you started in Cleveland, you would have done this route. One's better than the other. Both of them were a greedy local algorithm, the same algorithm run, but the answer depends on where you chose your starting point to be. So an interesting fact about greedy local algorithms is they give answers, but they can differ depending on A, the initial local point you choose. So is it going to give you a good answer? Well, we argue that greed is good for capitalism. We argue that local opinion is important for schools. But as a mathematician, I worry that using only some of the information was the best way to go. Maybe I should use all of the information. Well, before I go on to the use all of the information, I want to point out that this algorithm here that we just did has a very simple name to it. It's called the nearest neighbor algorithm. You're someplace and you simply ask the question, where's the nearest? I'm going to go there. Where near really means the least cost, the least time, the shortest distance, some minimization of whatever you're measuring. Because it's not always used on distance. It could be used on cost and time, other things of that sort. Now, it's not very hard to run this algorithm on fairly large problems. So I'm going to draw a fairly big picture here. And the first thing I'm going to tell you about this picture is we think of it as a road map that the numbers I'm going to put down are distances between 2 points. It really doesn't say the route. It just says somebody looked it up for you. So guess what? Every single city is connected to every other city. We can't say anything different because we know there is a way to get from one city to every other city. So because of this, there are just one heck of a lot of lines. In fact, if I got them all, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. This guy missed somebody. 1, 2, 3, 4, 5, 6, 7. Helps if I can count. Valent 7. 1, 2, 3, 4, 5, 6, 7. Valent 7. 1, 2, 3, 4, 5. Missed 2. Didn't get this guy. Didn't get this guy. 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Missed one here. 7, 7. 1, 2, 3, 4, 5, 6. Missed this one. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. When every vertex has exactly the same valence and they all connect to one another, this is called a complete graph. And because Hamilton problems are so hard, we only do Hamilton problems on complete graphs. These are not actually the roads. They are just a measure of distance or time or cost. And so it's a very important idea of how this is implemented. Now, if I put numbers on every one of these edges and you were here, you would just look at these 7 edges and say which is smallest and go there. And then you would repeat which is smallest and go there. But now this graph looks really complicated. I mean, if I fill in all these numbers, it's kind of crazy. So we have a different representation that we like. We like tables. So first off, we don't put in the zeros, says the distance or cost from A to A is 0, B to B is 0. And we assume like all directions are the same there and back, but it doesn't have to be. So I can put in numbers like this. So cost from A to B is 10, but then the cost from A to B is 10, 20, 15, 12. I'm going to put in 7, 7, 6, 6, 9, 9. 8, 8, 12, 12, 7, 7. That is a complete 5 graph. 5 vertices, every vertex connected to everything else, and the distance are the same whether we go from A to B or B to A and vice versa. Now I don't have to draw a graph of this to do the nearest neighbor. I can just start somewhere and say, well, I'm at D. What's closest to D? Well, read D's row and go, oh, B is closest, 6. And now I'm at B and say, what's closest to B? Well, D is, but we've already been there. So 10, 7, and 9. C is closest. B to C by 7. Now I'm at C. What's closest to C? B, but we've already been there. D, oh, do we want to go home right away? No, we want to visit every city. So we actually, this is a little sneaky when we're reading the graph. I've been to B, so I can't go back. But I could loop back to D, but I've got to visit all the cities. So that means it's between A and E, 12 and 20. So we're going to go to E for 12. So now there's only 5 cities. 1, 2, 3, 4. We're forced. Last city, A. That cost is E to A is 12. And then we're forced to go home A to D. A to D is 15. And there's our nearest neighbor done without actually drawing the map. We just listed our values. So these tables, they can really help speed things along. And since the relative relationship of A and B and all the other edges are not relevant, we're only interested in visiting every vertex, we've got this thing nailed. All right. Now it's time to do a global algorithm. A global algorithm that does something very important. The global algorithm uses all of the information and then tries to get to where we need to go. Now, global. All info. I want it to be greedy. How can I use all of the information? Well, one way is to look at every single edge and say, well, which is a good edge? Should I consider only using small edges, or should I consider using pairs of small edges? Well, I'm going to try simply to use a greedy algorithm where I just look at all of the edges and pick the smallest. The problem with that is I may not be at either city. So global, because it's using all of the information, and I'm going to try to be greedy here, it has no starting point. The solution slowly builds. You don't see the answer necessarily happening quickly. In fact, it doesn't even look like a circuit to begin. So let's begin with a picture. It's got to be complicated enough. So I'm going to get 5 cities here. There's the edges. So now I'm going to put in some of the roads here. So here's a 10. Here's a 12. Here's a 13. Let's put in a 9. And then we'll put in a 14. And then we'll put in a 11, another 13, and a 15. So let's see, didn't get this one. I'll make this one another 12. So I've got 1, 2, 3, 4, 5, 6. Yep, I've got all the edges now. So I need to give the vertices 8 names. That'll help me. A, B, C, D, E. And now this global algorithm says, let's pick the least edge and use it. So I'm going to order my edges. There's an edge 9, 10, 11, 2 12s, 2 13s, a 14, and a 15. I think I missed one. There's 2 13s. Yeah, there we go. So and I got all the edges in there. And this is how this algorithm now works. I hereby declare I'm going to use the 9, and I highlight it and say, when I finally go on this trip, I'm going to drive this route. I cross it out, and now I repeat, which is the smallest edge. Now I'm going to pick a 10. That's the smallest. And I highlight and say, someday I'm going to travel on that road. Now notice, my route that's building, my circuit, it's not even connected yet. There's like 4 endpoints. All right, let's keep going and see what happens. All right, 11's next. Can I add this and will it look like a route? Well, yes, it's going to look like this. This is allowed to be added. I use it. Let's see if I can do this 12. Well, I want you to notice if I add this 12 in, something strange happens. This 12 makes 3 edges come to this vertex. We're supposed to visit each vertex exactly once, so if we go in and out, that means we're coming back in or coming out another time. So I can't use that edge. Don't highlight an edge where the valence of the highlighted graph goes up above 2. So we're not going to use this 12. Nope. Look at the next 12. Can I use this 12? And the answer is, nope, we can't do that one either for a different reason. This one, too high of a valence at this edge D. But this 12 is thrown away because it makes an early circuit. We miss B. So I want you to notice this global algorithm, it's harder. It's using more information, and I have to know the rules of it better. These are the only 2 difficulties to look for. Don't have too high of a valence. Don't make an early circuit. So we're not going to use this one. So far we got this edge, and this edge. Let's try one of the 13s. Well, if we try to do this one, nope, that makes a valence 3. Bad. Can we try this 13? Nope, that makes a valence 3. Bad. Wow. What's happened is the 14 is being forced on us, and the 15 is being forced on us. And there's our circuit. It goes like wherever you like to start. Let's start at A. Let's go A, B, E, C, D, A. A, B, E, C, D, A, and we got home. Is this a good path? I mean, good circuit? The answer is we really don't know. Why? Because the Hamilton problem is hard. We use massive computers, but this can be done quickly to get an initial solution that we can work with. You got to get the salesman on the road. Imagine if you had 50 cities to visit. You can't spend 4 days before you get him on the road. Heck, he could already visited 5 of the cities, and you don't necessarily know if your computer is going to stop. So, these algorithms, the nearest neighbor algorithm, which is local, greedy, the sorted edge algorithm, that's the one we just did. We sorted the edges. It is global and greedy. First off, I want you to notice it doesn't have a dead person's name attached to it. That's kind of like a standard in mathematics. When somebody produces a good idea, they slap their name on it. Euler's theorem, Einstein's theory of relativity. When somebody produces something that's amazing, we put a name to it, not just a description. When you see in this course descriptions of algorithms with nobody's name, that means these algorithms produce a very special kind of solution. We call them feasible solutions. It simply means, feasible means it's a solution. I mean, this is terribly redundant. I have a solution. But feasible means we don't know if it's good. Could be a great solution. We just don't know yet. So many times people produce solutions and then we evaluate if they're good. If 2 people have solutions, we evaluate them both and see which one's better. But by no means do we believe that these algorithms are producing great answers. In general, we kind of believe that the sorted edge algorithm is better than the nearest neighbor because it's global and greedy just like the local. But it's not hard to construct an example where the sorted edge fails miserably and the nearest neighbor does better. They don't behave exactly as we expect, other than that they produce answers. All right, there is our beginnings of Chapter 2. We're going to do some much more in Chapter 2. And the assignments from Chapter 2, first half, let's call it 2A, because we did first part of A, we did the second part of A. Let's call it 1A. Sorry, Chapter 1, we did 1, and then we did another part of 1. We'll call it 1A, 1B. This is 2A. And guess what? We're going to have a 2B. We're going to do this a lot in the chapters, break them in half. We're going to submit our homework in general a whole chapter at a time. So look for the email explaining the submission rules. So here we go, our exercises. First, I just want you to look at one that you can find the answers for. So I'd like you to do problem number 1. This is just like a build-up. But then problem number 2, which you can't find the answer for. Next, problem number 8. Now, problem number 8, it's not a nice problem to ask a young student to do. I'm asking you to write English sentences about mathematics. That's not nice, but give it a try. Problem number 12. Problem number 36. Problem number 40. Problem number 46. And problem number 50. So there's our assignment in Chapter 2.